Johnny here with Simpson Math. In this video, I'm going to be talking about sequences, kind of introducing you to them and a lot of maybe some new vocabulary. Now, we are in the Calculus 2 setting, so that means we just kind of finished up a portion of the class where we were discussing continuous functions. So we were integrating some nice continuous stuff. So even calculating the volume, we would, talk about the y-axis or the x-axis, that those real numbers were being mapped to other real numbers. Nice continuous data, continuous functions. This next portion, we'll be talking about discrete math. And so it's more pinpoint, not continuous. I'll get more into that later. For now, let's start talking about sequences. And when someone first mentions a sequence, I just go back one more step and I say, well, a set is a list of objects, typically in math, a list of numbers. A sequence is a little bit more direct. It is an ordered list of numbers. So there's an order to it. All right, let me just put down an example of a sequence. Something like 1, 2, 3, 4, 5. I think you get the picture, ... And I can keep going. And then I could even talk about the nth term of this sequence. And I can just continue and continue and continue. So this sequence is indefinite. It goes on forever. I'll have a 100th term, and that n will just keep getting bigger and bigger. And there's an order to this. The numbers seem to be increasing by 1 every single time. All right, some notation. A sequence, we have a common notation for a sequence, and that's a sub n. So a is the name of the sequence, and n, we'll talk more about that in a little bit, but that's the like a starting index or the index, but it's just the nth number basically. And for this sequence that I just mentioned, the same notation, 1, 2, 3, ... So we have this sequence a sub n, and it is the sequence 1, 2, 3, and then the ... just means that this behavior continues. So that supposedly in these three numbers, we should be able to see a pattern, and that pattern will continue forever. Now, there is a little bit more notation I could throw in here. I'll talk about it more later in this video or maybe in another video. I might as well just introduce it to you now, though. We did say the word set, so we could use those set braces. And then this sequence will start when n is 1, and then it goes out to infinity. So this is it's the same notation. We're talking about the sequence a sub n, but this goes a little bit further to say we're starting at 1 and we're going out to infinity. I'm going to drop that for a little bit and I'll come back to it later. But I wanted to just go ahead and say it now. Okay, I'm going to write down this right here. A sub 8. What does that mean? In fact, what is a sub 8? Well, this is just saying there's a sequence out there called A, and I want to know the 8th term of that sequence. So the A sequence is written right here, and I want to know what is the 8th term. Now, term, what is a term? Well, back in this sequence, these are terms. So n is the nth term. 1 is the first term. So what's the 8th term? Well, this sequence is kind of obvious. It's going to be an 8. So a sub 8 is equal to 8. And I think this is obvious too. What's a sub 13? What's the 13th number of the 13th term of the sequence? Well, I know the pattern here. It's going to be 13. And a sub n is just going to be n. Now, we're using n on purpose here. Not k, not p, not x, anything like that. We're using n as in the natural numbers. This set that we've just, or this sequence that we just were discussing, those are the natural numbers. It starts with 1, and then it's 2, 3, 4, 5. So remember earlier I was talking about continuous versus discrete. This is discrete because we're not including all of the infinite numbers of numbers between 1 and 2. So we're not talking about 1.3 and 1.3 repeated. So n in this game, or a sub n, is the natural numbers. We write those number systems with double bar letters. It's supposed to be a double bar n. Yeah, the natural numbers. All right. So that's one way to talk about a sequence. Just list the first few terms enough that a pattern is supposed to be recognizable, and then ... That's a little tedious maybe. So there are other ways we can write a sequence. One is called a closed form, and it's very powerful. The closed form is basically a formula that spits out the term that you want. A formula that describes a sequence. There's also a recursive form. And though not as powerful as the closed form, the benefit of the recursive form is it's easy. The recursive form is based off the previous term in the sequence. I'll say uses previous term to define the sequence. I'm not sure why I'm writing so small, but closed form, think of it as a formula that describes the sequence. The recursive form is another way to describe the sequence, but it uses the previous term. So what I mean here is, again, it's another way to write a sub n. The closed form is a formula, and we have it written right here because this one's so simple, where the formula is just n. If I plug in 1, well, that's the first term of the sequence. If I plug in 8, well, that's the 8th term of the sequence. Nice and easy in this case. The recursive form uses the previous term. So a sub n, well, let's use this 3. How did I get 3 from 2? So a sub 3 would be the a sub 2 plus 1. So now I'm going to go in more generic form. A sub n would be the n minus 1 term plus 1. Write that down and then let's see if that makes sense to you. A sub n, that's the nth term of the sequence. In this case, that's the name of the sequence. A sub n minus 1, well, this is saying the previous term, if I add 1 to it, that's going to give me the current, or the one I'm after, the one I'm looking for. Recursive form, closed form. Let's do that again. Let me make it a little bit more complicated so it's not so obvious. But I'm not going to make it too hard. Let's have another a sub n sequence. This one is 2, 4, 6, 8, 10, 12, ... I think you get the picture. Let me just move my Dr. Pepper off camera. All right. That looks good right there. Okay. So let's just ask those same questions. What is a sub 8? What is a closed form of this sequence? That is, can I come up with a formula that will give me any term that I'm looking for, and then a recursive form. That is, supposedly it's an easier way to define the sequence. All right, so the a sub 8. Well, this is 1, 2, 3, 4, 5, 6. Now, notice what I'm doing there. I'm thinking of 2 as the first term. I'm thinking of 4 as the second term, and so on. What I'm doing there is something I'll talk about in more detail in a little bit, but I'm indexing this sequence. I'm saying this is the first term. This is the second, third, fourth, fifth, sixth, seventh, eighth, and so on. Actually, I don't have 7 and 8, but and so on. And these indexes can be a great tool for coming up with a formula or a closed form of the sequence. The indices, the plural for index is indices, those indices can sometimes help us create that closed form or come up with a closed form of the sequence, or maybe as an explicit form. Okay, so I think I can just continue this pattern and determine that the 8th term would probably be 16, because it seems like I'm just adding 2 every time. So the 7th term would be 14, and the 8th term would be 16. Let's see if I can maybe come up with a recursive form and closed form that verify it, or I don't know, agree with that. And I claim I'm going to start with a recursive form because it's supposed to be easier. So, recursive form. How am I getting the next number? So the second term in this sequence, 4, what did I do to the 2 in order to get to the 4? Well, maybe I squared it. Maybe I multiplied it by 2. Maybe I added 2. There's 3 different possibilities there. Let's add the 6 in there. Now it's a little bit more obvious that we're not using powers. We're not using multiplication. We're just simply adding 2 to the previous term every single time. So I think the recursive form a sub n is you take the previous term. So I'm looking for the nth term. Well, I take the previous term, whatever it is, and I'm going to add 2 to it. The previous term plus 2. So the recursive form is, of course, a sequence a sub n. It always uses the previous term to get to it. So this one I'm just taking the previous term plus 2. Okay. Now a closed form. Well, previously it was just in. If I plugged in 5, it gave me the 5th term. This time not so obvious. When I plug in 1, I get 2. The second one gives me 4. The third one gives me 6. Fourth one gives me 8. Okay, well, I'm thinking we're dealing with even numbers, adding 2, starting at 2. Let's see if I can come up with maybe a way to describe this. Let's see. The 6, 2, 4, 6, 8, 10. Well, actually, this is just the even numbers. So if I just take that first index and kind of, I don't know, multiply it by 2, I get that every single time. 2 times 2 is 4. 3 times 2 is 6. That could be helpful. So maybe I'm just doubling in. Oh yeah, that makes a lot of sense to me. So if I just say 2n, let's see if that works. The first term, 2 times 1 is 2. Yeah. The third term, 2 times 3 is 6. Yeah. Okay, so I'm just doubling that indice. So the indices may help in some cases. I wrote them down, and then I was able to like mentally think about it a little bit. It wasn't as obvious to me maybe as it was to some of y'all, but the first term was doubled, the second term was doubled, and so on. So then the 8th term, I'm going to use these 2 forms to come up with it. Oh, now this one, I need the 7th term in order to find it. Okay, well, let's find the 7th term. The 7th term, a sub 7, would be a sub 6 plus 2. So that is 12 plus 2, which is 14. Now I can go further and say, well, now a sub 8 is a little bit tedious. You can see how the recursive form is not as powerful. That uses a sub 7 plus 2. So I have 14 plus 2, and that gives me the 16 that I'm pretty sure I'm happy about. And if I plug in 8 into the closed form, 2 times 8 is 16. Yes, the 8th term of this sequence is 16. Recursive form, easier to talk about, easier to find, less helpful. Especially if I want to find the 100th term of this sequence. There's no way, I would have to find the 99th, the 98th. That's going to take too long. So the closed form is way more powerful. Let's do another one very similar to this. Starting at 0, 2, 4, 6, 8, 10, ... Looks very familiar. Even numbers, just like the last time. The only difference is this sequence starts at 0. The first term is 0. But let's ask the same questions. What is the 8th term of this sequence? Can we come up with a closed form? Can we come up with a recursive form? I think I'm going to go this order. Recursive form is a little bit easier for me. And this is very similar to last time. To get from 0 to 2, I'm adding. To get from 2. To get from 2 to 4, I'm adding 2. To get from 4 to 6, it's the same thing. The nth term of the sequence will be the previous term plus 2 again. Let's see here. A closed form. Closed form is more of a formula, very strong. 2n worked last time, but if I try that again, 2 times 1 would not give me this 0. So I need to somehow come up with a way that I start at 0. I could do 2n minus 2. That may work. Let me go back to the indices one more time. I'm thinking of 0 as the first term, 2 as the second, 3, 4, 5, 6. This can maybe help me see a closed form. I'm looking at, I don't know, not one of the early ones, but maybe the 6. And I say, hey, that came from, or that's 2 times 3. We were doubling last time. 4 is 2 times 2. 8 is 2 times 4. So 6 is the third term of the sequence times 2. So that a way to say that is we take the, let's see, 2n is not strong enough. So what I'm looking for here is 2 times the previous one. That's n minus 1. There we go. So if I take 6 times 4, or the 4 times 2, sorry. 4 times 2 would give me 12. That's not what I have here. It's the previous index that I'm going to multiply by 2 by. So 4 minus 1 is 3. 3 times the 2 gives me the 6. I hope that made some sense to you. But I said it earlier. Another way for the closed form, if I could distribute 2n minus 2. So it's that if n is 1, the first number in the sequence. So the first one is 1. 2 times 1 is 2. 2 minus 2 gives me the 0. Let's plug in a 2 for n. So notice these indices are the n's that I am using in my formula. Okay, 2. 2 times 2 is 4. 4 minus 2 is 2. 2 times 3 is 6. 6 minus 2 is 1. 2 times 4 is 8. 8 minus 2 is 6. Okay, I like it. Closed form, 2n minus 2. So if I want to find the 8th term of the sequence, recursive form would require the 7th, which I suppose is 12, so I would get 14, okay. The closed form would be to take 2 times 8 minus 2. 16 minus 2 is 14. They both agree. 14 must be the 8th term of this sequence. Okay. Ooh. Now let's find the 199th term. Okay, I am for sure not going to go through the recursive work. I'm going to use the closed form. 2 times 199 minus 2. I think that's going to be shy of 400. So this is 398 minus 2. I get 396 as the 199th term of this sequence. Okay. So here on this page of notes, I'm just trying to get you familiarized with the vocabulary and maybe the notation. Hopefully that helped. Now there is a famous sequence out there called the Fibonacci sequence. You've probably heard of it, but I'm going to talk about it real quick. Now this is so famous, instead of using A sub n, I'm going to call it F sub n. This is the Fibonacci sequence. And I'm going to start it off at 0, 1, 1, 2, 3, 5, 8. I think a pattern is obvious in here, or at least enough to define one. So I'm going to put a dot, 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 and this sequence goes on forever. If you're unfamiliar with the sequence, well, I'll talk about it when I get to the recursive form. But I have the same questions. I want to know, what is the 8th term of this sequence? The closed form. And then a recursive form. So this is 1, 2, 3, 4, 5, 6, 7. So I need to just know what is the next term in the sequence to find the 8th term. Okay, so we start off with 0 and 1. And then if I were to sum those two terms, I would get 1. If I sum these two terms, I get 2. If I sum those two terms, I get 3. If I sum those two terms, I get 5. So on and so forth. So the recursive form is how the Fibonacci sequence is explained. The next term in the sequence is the sum of the two previous terms. So if I want to know a recursive form, Fn, well, I take the previous term and I add it to the term before that. So I'm going to call that f sub n minus 2 plus f sub n minus 1. So for this sequence to even begin, I do have to start with 0 and 1. For the recursive definition, you have to have at least those two terms to start off with. But if you have 0 and 1, and then you start to add, and you get this sequence. So then what is the next term in the sequence? Well, f sub 8 would be f sub 6 plus f sub 7, which is 5 plus 8. That's going to give us 13. The 8th term in this Fibonacci sequence is 13. Now, closed form, we're not going to get into that anytime soon. I'm going to say here, damn, near impossible. You can maybe study that later in life. I don't know. Okay. But the Fibonacci sequence is a famous sequence, and it's basically from this recursive definition. Okay, don't worry about a closed form. I think now what I'd like to do is just play around. I'm going to put some sequences down here and kind of see if you can come up with the pattern. This is a lot more fun in my in-class courses. I kind of like group people up and see if they can have little contests and stuff. But here you can pause the video and get stressed about it. So I'm going to put down some sequences here. A sub n is 1, 4, 27, 256, ... Let's get about 4 lines or so. I have another sequence B, and it is 3, 1, 4, 1, 5, 2. Make sure, no, that's not right. 9, 2, that would be really bad. Let me double check that. 3, 1, 4, 1, 5, 9, 2. Yeah, something like, okay. C, skip a few lines. Another sequence. Let's do 1, 1, 1, 2, 1, 1, 2, 1, 1, 1, 1, 1, 2, 2, 1, ... I'll put a fourth one up here. Sequence D, which is 3, 3, 5, 4, 4, 3, 5, 5, ... So I'm very curious if you are, I don't want to say clever, if you are clever enough to find the 5th term of the A sequence, the 8th term of the B sequence, the next term or the 6th term of the C sequence, and the 9th term of this D sequence. So I don't want you to come up with a recursive form. I don't want you to come up with a closed form. Just can you see a pattern and come up with the next term? I'm going to write down some hints, and then you can maybe pause the video and try it out. Maybe kind of hard to say or read. The first one I think is maybe a little bit obvious, so no hints. The second one, or actually the next 3, they're not arithmetic, so there's not any math involved. There's no multiplication or addition, anything like that. They're just silly patterns. First one maybe has to do with food. The second one, I read this one uniquely, so maybe go back and watch or listen to me read it, or read it out loud. And this one, indices may help. Did I spell that right? Indices. Yep. All right. You got this. Pause the video, go. All right. The first one, well, these are perfect, not perfect squares, but they're like powers. This is, if I think about indices again, 1, 2, 3, 4. Yep. This is 1 to the first power. 4 is a lot of things, but it's 2 to the second power. 27 is 3 to the third. And 256 is a power of 4. That's 4 to the fourth power. So notice I'm just taking n and raising it to the nth power. So I'm just going to call this 5 to the fifth power, which is 3,125. So a closed form here, I didn't ask for it, but this was easy-ish. It's n to the n. You'd have to be some cleverness to get a recursive form, because you're not adding, you're not multiplying, you're doing something clever. I probably don't ask you to find a recursive form there. All right, the next one. Do those numbers look familiar to you, especially the 3, 1, 4? These are the digits of pi. So if you don't have the digits of pi memorized out that far, you can just plug it into the calculator. And it looks like the next one is a 6. Nice and silly is all that is. I hope you didn't stress too much about that. Okay, the next one is even crazier. Listen to me read it out loud. The first term is 1. This is 1, 1. This is 2, 1. This is 1, 2, 1, 1. This is 1, 2. Did I do that right? Yeah. 1, 2, 1. I'm sorry. Do it again. 1, 1, 1, 2. There we go. 2, 1. Whew, that's pretty hard. Okay. So I'm just, this is super silly, but let's see if I can do the next term. I'm going to have 3 1s, 2 2s, 1 1. All right. Fun times. Then this one here, I claim indices will help if you haven't seen it yet. It does look really cool because it has this double number. So you may think about it for a little while. It's like you repeat the number and you add 2. You subtract 1, repeat it, subtract 1, you add 2 and repeat it. There's not quite a pattern yet for math involved. But I do have a hint of the indices. So I'm going to write out the indices. This is 1, 2, 3. Maybe you're catching on. I'm not writing 1, 2, 3. I'm writing the words 1, 2, 3. And that's the number of letters in the English language accordingly. So the next number, let's see, 3, 4, 5, 6, 7. I did that wrong, but that's 9. 1, 2, 3, 4, 5, 6, 7, 8. I need the 9th term. Well, there are 4 letters in the word 9, N-I-N-E, so it's 4. Okay, those are silly. I just wanted to play for a little bit. Let's now move on. Yeah. Next, I'd like to talk about the golden ratio. That's the Greek letter phi. The golden ratio is a lot like like pi. It's an irrational number. And there's so much I could talk about with the golden ratio. I would love to just have a whole video series on this thing. I encourage you to just like Google or YouTube search golden ratio, go down that rabbit hole and just watch videos for hours. It's very cool how it pops up in math, of course, and how we use it in architecture and paintings, and you see it in nature. Yeah, but for our purpose, I want to at least introduce you to the number phi, and the way I'm going to do it is I'm going to talk about the golden section. All right, so the golden section divides a segment into 2 sections so that the ratio of the larger segment to the whole section equals the ratio of the smaller section to the larger. Okay, that's probably meaningless. A picture here is going to be worth 1,000 words. Let me go ahead and draw a line segment. I'm going to label that AC. And I'm going to put a B in here that makes this golden section, this divine relationship. And it's going to be about right there. Okay, this is beautiful. I know you see it too. And so in words, what I'm saying here is the smaller BC is to the larger AB. So this segment is cut into a small part and a larger part. BC is to AB as AB is to the whole segment. So in symbols here, I could say AB is to the whole AC as BC is to the larger AB. And this pops up so often, we call this the divine proportion. It's pleasing to the eye. You can look for it in nature. One area is my face. A beautiful person, they would have this golden ratio all in there. So you can think about the distance from my chin to the eye as the AB, the larger segment, and then my face BC. That's the eye distance, probably to the top of my hairline. I got a really big forehead, so I'm not all that beautiful, but you can imagine that those proportions, if they line up just nicely, they're very pleasing to us. And we paint that way. So our portraits, we try to create this ratio. Our ancient wonders, our ancient buildings like the Temple of Zeus and the Parthenon, we use this golden ratio. Okay. To come up with it, I'm going to put some values in here, and I can do this several ways. Because the AB is used twice, I think it'll be more convenient for me to let AB equal some pretty number like 1. I'm going to let AB equal 1, and then the entire thing, AC, that's kind of what I'm going after. I'll let that be X. Well, if the entire thing is X, and the larger piece is AB, then I can find the smaller piece by subtracting AB from AC. So I claim I know then that BC would be the whole thing, X minus the larger thing, 1. And I can set up this proportion. 1 is to the whole X as the smaller piece, X minus 1, is to the larger piece, 1. Now I'm just going to solve this equation for X. I think I will go through and multiply through by the LCD X. And I'm also going to flip-flop my equation just for convenience. So I'm multiplying through by X. So on the left, I'll have X squared minus X. On the right-hand side, well, the X is reduced, leaving me with 1. I can solve a quadratic a few ways. I just taught in pre-cal completing the square, so that's really on my mind. So I'm just going to do that. I'm going to complete the square. That is, I kind of rewrite it. I'm going to add a number in here, squared, and I'm going to do that to both sides. And the number I'm adding is going to make this a perfect square trinomial, so it's going to be half of this coefficient. So half of -1 is -1/2. When you square that, that's just a positive quarter. So on the other side of the equation, to balance out the equation, I need to add that quarter. Left factors nicely to x minus 1/2 whole squared, or quantity squared. I can get a common denominator that's 4 over 4, so this is 5/4. So far, not too bad. Now that I have that's cute, to get rid of the square, I can square root both sides. On the left, the square kind of undoes itself. of x minus 1/2. On the right, I could take the square root of the numerator separate from the square root of the denominator. It's an old exponent property. So I have the square root of 5 over 2. They have a common denominator, so when I add them over, that's going to be nice. And I get x equals 1 plus root 5 over the common denominator 2. This value is the golden ratio. So let's just get an approximation for that. In fact, let me call that phi. And then put a little it's approximately equal to. And then it is 1.61803398 ... some irrational number about 1.6. All right. So if you go back and you redo this exercise, but you let the whole be 1 and AB be x, you'll see something very nice. You get a 0.6, you get the same value but without the 1, the 0.6. So if AC were 1, this distance here is about 0.61, making this 0.39 or whatever. So that golden ratio of 0.6, sometimes you'll see it as 0.6180333 la la la, or sometimes you'll see it as 1.6. It kind of depends on how you're talking about the golden ratio. And that's what makes the golden ratio so cool, is it's kind of like the same up and, like, if you flip it around, the reciprocal. Anyways, okay, super cool. Okay, that is the golden ratio, 1.618. Go watch some golden ratio stuff. It's really cool. Let's see what I want to do next. All right, let's go back to sequence talk. Let's see if we can just find the next term in the sequence that I'm about to write down. I'll call this sequence A sub n. Starts off as 1, 2, 3 over 2, 5 over 3, 8 over 5, 13 over 8. I think enough is written down to get a pattern out of that, ... So do you see the pattern? If so, what's the next term in this sequence? What's the 7th term? If you don't see it, that's maybe okay. Let's look at the top numbers here. 1, 2, 3, 5. Okay, the 3, 5, 8, 13. That should be kind of familiar. We just talked about the Fibonacci sequence. So if I add 1 and 2, I get 3. If I add 2 and 3, I get 5. So these numerators are being, like, that's just the Fibonacci sequence, starting at 1 and 2. The denominators. Oh, there are denominators down there. I'm going to pencil kind of. Sometimes it helps to write these integers as ratios. So they have denominators. Oh, yeah, and if I do the Fibonacci here, 1 and 1 makes 2, 1 and 2 makes 3. So it's just a ratio of the Fibonacci numbers where the top is maybe the Fibonacci number and the bottom is the previous Fibonacci number. Okay, interesting. So what would be the next one? Well, the next number in the sequence, I would take the next one divided by the previous one. Let's see if I can write that down. F n plus 1 divided by f sub n. That's the future Fibonacci number divided by the current one. Let's see if that makes sense. If I had my notes, I should have played with them. Let's see, 1, 2, 6. Well, if I just do the Fibonacci number at the top, I'm going to get 21. And down below, I'll get the 13, the previous one. So the next number in the sequence is the future Fibonacci number divided by the previous Fibonacci number. Let's see if that makes sense to me. Just Fibonacci numbers. The fact that I didn't start at 0, does that matter? 1, 1, 2. I think this works. Maybe a more elegant way to say recursive form here. Or, I'm sorry, the closed form. Alright, but I think with the pattern I was able to tell, we're just getting the Fibonacci numbers, and it's always going to be the previous one down below. Okay, now let's look at that sequence one more time. I'm going to plug these values into a calculator to get a decimal approximation to see what's going on here. Well, the first one's clearly 1, 2, 1.5, 5/3. I've never been good with those thirds. There's like a repeating thing going on here. But I get 1.6 repeated. So this is, it started at 1, jumped up to 2, went down to 1.5, went up to 1.6 repeated. 8 divided by 5. Sorry. I get 1.6. That's a nice number. 13 divided by 8. 1.625. Look, this is an interesting thing. We're kind of hugging 1.6. Let's continue. The next term, the 7th term, was 21 divided by 13. 1.615384, and that repeats. And the previous thing, that's good. Maybe do you see some kind of number that it's approaching? We just talked about the golden ratio. That golden ratio is about 1.618. This sequence, the Fibonacci divided by the previous Fibonacci, that sequence approaches a number. Now there's a lot going on in what I just said. Not only is this some neat, cool sequence, but this should be reminiscent to talks we had earlier in the semester, or even Cal 1, when something approaches a number. What are we talking about when we kind of dance around that phi number? 1.6, 1.62, 1.65, 1.63, 1.64. What's that idea of approaching? Hopefully the word limit is kind of ringing a bell here. All right, I'm just going to put some words here. I say the terms quickly. Make it to 1.6 and then dance around 1.618, the golden ratio. Are they going somewhere? Are the terms going somewhere? More mathematical way to say that is, are the terms approaching something? If I'm approaching something, then I'm talking about, are they approaching a number? Am I approaching a number? If so, then what they're doing is they are approaching an L, a limit. If they are not approaching a number, so like a sine wave, or like the digits that just pop around up and down, like as if they were a sine wave, that would diverge. It would not come to a limit. If the sequence just goes up and up and up and up, that's not approaching a number, that's approaching infinity, so that doesn't have a limit. We say maybe it's divergent. I'm introducing new terminology into this sequence world. Don't get confused, but I think it should be very familiar to you. It should kind of be comfortable. I'll put this in math notation that should be very familiar to you. I'm going to say the limit as the indices, so as those n's approach infinity, as n goes out to infinity, of a Fibonacci number divided by the previous Fibonacci number approaches the number phi. All right. So these sequences, most of them, well, I won't say that. But these sequences are kind of cool. And some of them, if they approach a number, then we can start talking about limits of the sequences and what they actually approach, or if the sequence diverges. All right, what do I want to talk about next? Oh, before I move on, remember the very beginning of this, I talked about another type of notation for this sequence. Maybe I'm about ready for it. So this sequence, a sub n, another way to talk about it or write it is this notation here, where you put it in those like set braces, and we start at n equals 1 and we go out to infinity. It kind of helps with the idea of we're taking those n's out to infinity. So these natural numbers are these indices here. They're the natural numbers. They are discrete, but they're mapping to the real number system. And this sequence, we start at 1 and we go out to infinity. And as we evaluate the limit of the sequence, as n goes out to infinity, that sequence approached phi. Okay, let's move on to more talk about indices. So let's talk indices. That's the plural of index. Now, we can change the indices, and that's called indexing. So far we've been talking about the natural numbers. They make most sense to all of us. So I can get a better script in here. Natural numbers. So this is of course the first term, second, third, fourth, fifth, and so on. But we can change these indices. So right now, my index is 1, and that corresponds to the first term of the sequence. Well, we can just index this. We can change our indices. So I'm going to write a script or a double bar whole or W for, I wonder how you do that. All right. Put a double bar W for whole numbers. Those are the natural numbers, but 0 is included. So the first term is actually 10 if I re-index this. Okay, that's confusing, but let me explain what I mean by that. I'm going to come up with some forms using n as my index and using w as my index, I guess. So up here, I would have, well, let's think about how can I talk about this sequence, its closed form. So how can I turn 1 into 2? How can I turn 2 into 8? Every time it looks like I'm just adding 8 every single time. That's not too bad. But how can I come up with a closed form here? I claimed earlier that if I use indices, it kind of helps me with the closed form. So maybe if I'm adding 8, I multiply by 8. So 1 times 8 minus 6 would give me 2. 2 times 8 is 18 minus 6 does not give me 10. Never mind. How about if I do, again, 1 times 8 is 8 minus 6 is 2. 2 times 8, oh, it's 16. What did I say earlier? Okay, yeah. I like that. This is going to be 8 times n minus 6. I think that works. For the third term, 3 times 8 is 24. You subtract 6, you get 18. Yeah. Okay, now down here, if I re-index it, if I change my indices, then I claim I could do something like this. Should I change the n, I wonder? I think I'm going to leave it in. But here, I've changed the index. So 0 is like an initial term, and n equals 1 is the first term. So confusing, but don't be confused. Okay, how can I come up with this same sequence, but instead of starting at 1, I'm going to start at 0. So that's the notation I need to use here. This is the set of a sub n, where I start at 0 and go to infinity. The one I just did was the set of a sub n, where I start at 1 and go to infinity. Sorry, it's kind of crammed in there, but I thought that may help. Purple, 1 to infinity. Here I'm changing the indices. I'm indexing. I'm changing the index. Okay, well, I think it's going to be very similar. I'm just adding 8. So if I do 8 times 0, though, I get 0. So how about 8 times n plus 2? 8 times 1 plus 2 is 10. Yep. 8 times 2 is 16. Yeah, that works. So this time I'll have 8 times that n, but it starts at 0. So 8 times 0 is 0, and I add 2 to get that first, or that initial term. Again, if I wanted a sub 1 for both of these, a sub 1 is talking about the first term here, 2, whereas a sub 1 in the second version is a different story. This is talking about 1. I'm sorry, 10. I'm going to that brace notation. Okay, that probably wasn't clear, but I'm going to pretend like it was and move on. Let's see. This can be helpful when coming up with some closed forms. Sometimes it's easier to start off with a 0. So this is an option when you're trying to come up with a closed form. Okay, I'm going to do some vocab here, and then maybe show an example. So let me just write this down. every term after the first in an arithmetic sequence is the arithmetic mean of its adjacent terms. Its adjacent terms. Now you know what arithmetic mean, that is, you sum up and divide by the numbers. So I claim in an arithmetic sequence that every term is the arithmetic mean of their adjacent terms. So I could, like this one above, we call it arithmetic sequence because we're just adding, arithmetic, like just adding here. So I'm adding 8 every single time. So I can do this one in my head. 10, the two adjacent terms are 2 and 18. If I add those, I get 20. If I divide by 2, I get 10. That's called an arithmetic sequence. And they always have this arithmetic mean. So when you're adding 6 every time, another way to talk about it is that, like, you may want to look at the products to see some stuff. All right. Moving on. Let's do another example here. Well, maybe that comes into play. I have a sequence b sub n, but this one starts at 0 and goes up to infinity. So I'm now using this notation because I really need to show that I'm not starting at the usual 1 that we have been talking about all video long. I've re-indexed it, so it's going to start, or n will start at 0. And this sequence is 1, 9, 17, 25, 33, dot, dot, dot. Hopefully we can maybe see a pattern. I think 8 this time. 1 plus 8 is 9, 9 plus 8 is 17, and that pattern continues. 25 plus 8 is 33, and so on. So as an example here, I would call this an arithmetic sequence, and 25 then should be equal to 17 plus 33 divided by 2. If I add those together, that's a lovely 50. Yes, it does equal 25. Cool. All right, now if I want to come up with a closed form of an arithmetic sequence, and the index starts at 0, I claim it's going to be quite easy, because all you do is you multiply by that sum, that difference basically. So the difference here was 8. The difference here is also 8. So it's going to be 8 times n plus that initial value 1. Let's see if that makes sense here. Closed form of arithmetic sequence. A sub n equals that initial value at a naught or a0 plus d times n, where d is the difference. So I claim if you have an arithmetic sequence and you're trying to come up with a closed form and maybe you're having difficulty, one option is to re-index it so that n starts at 0. Then you can always just apply this basically formula. So I claim back to this sequence, b sub n will be equal to that initial value, which in this case is 1, plus the difference. Well, the difference every time is just 8 times n, or 8n plus 1 probably. Let's just maybe confirm this. I want to find the fifth term. Does it really equal 33? The fifth term of the sequence b or actually, oh, that's technically not the fifth term, but let's find b sub 5 here. That just means we take 1 plus 8 times 5. 1 plus 40 is 41. Oh yeah, look what happened there. 1, 2, 3, 4, 5. I got confused, so I'm sure you are too. So by indexing it, the first term is no longer the first term. That is now a initial term. So by re-indexing it, this is a initial term, and this is n equals 1. So if I want to find the fifth term, well, the formula holds true. I'm going to have 41 next in my sequence. But notice it's not what we have been calling the fifth term in the sequence, because I got 1, 2, 3, 4, 5 numbers before it. But that's because we pushed everything back. N now starts at 0. 1, 2, 3, 4, 5. Okay, I hope that made some sense. I'm going to do that again for geometric sequences. And maybe the second time around it'll make a little more sense. Okay, I'm going to start off something similar. I say every term after the first in a geometric sequence arithmetic, let me come back here and just say what I mean here is addition. Arithmetic sequences are you're just adding, or maybe you're subtracting every time, but it's just that addition is going on in every step. Geometric is multiplication, so you're multiplying by a number every single time. So in an arithmetic sequence, every term, the two adjacent numbers, if you found their arithmetic mean, you'd get that term. Here, it's a geometric mean. Now, you probably haven't worked with that before, so let's play with it. Here is the geometric mean of its two adjacent terms. Let me put a sequence down here. I'll call it G sub n. I'm going to index it. I'm going to start here at 0 and go into infinity. By re-indexing it, by indexing it, changing the indices, starting at 0, I think the closed form will be nice and convenient, like it was with the arithmetic sequence. This sequence starts at 1, 3, 9, I think you see the pattern, 27, 81, and so on. So notice every time I'm just multiplying by 3, times 3, times 3, times 3. So the recursive form is easy. To come up with a closed form, it may help to talk about the indices. Now the indices start here at 0, 1, 2, 3, 4. So it looks like I could maybe 3 times 0 plus 3. No. 3 times 1. No, that makes sense. 3 times 0. Or 3 times n. 3 times 0 is 1. Oh, no, that doesn't work. Plus 1? No, that doesn't work. Let's see. Oh, yeah. Oh, yeah. Think about it as powers. This is 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. 3 to the 0 power is 1. That'll work. Now, I didn't mention the geometric mean, so let me talk about that real quick. I'll use 9, I suppose. 9 is the geometric mean of the adjacent terms 3 and 27. If you ever need to find the geometric mean, you take the two numbers, you let's see, you square and then add and then square root. No, you just multiply and square root. Oh my goodness. The adjacent numbers to 9 are 3 and 27. I'm going to multiply them together and then square root. Okay, yeah. So 3 times 27, that is 81. Square root of 81 is that 9 that I was looking for, yes. Even I haven't worked with the geometric mean that often. I got a little confused, but there you go. That's always going to be the case for these geometric sequences. If you take the adjacent terms, you multiply them together and find the square root, it'll be that equal to that term. Let's do that again. 3. I take these two terms, 1 and 9, and multiply them together. I get 9. The square root of 9 is 3. I'm not a mathematician. 3 times 81 is 729. That does look familiar. The square root of 729 is 27. Good. So I don't know if you need to know those terms necessarily to do the homework, but I just wanted you to see that it's always true for these geometric sequences. Just geometric sequence is just a sequence where you're just multiplying by this common ratio every single time by 3. And I gave away the closed form earlier. You're just going to take the ratio of whatever geometric sequence you're talking about and raise it to the nth power. Oh, but I need to multiply, I think, by the initial term. Yeah. Just like in the arithmetic, you take the initial term, a0, and add the difference times n. In the geometric, you will start off with the initial term and you'll multiply by the common ratio to the nth power. So for this game, our initial term is 1, and I'm multiplying by the common ratio, which is 3 to the n. That was confusing to me because it's just so obvious. 3 to the nth power. I think what I need to do is more examples to help us out. We need to find this. Let's do examples. I need to practice. Let's state the closed form of some sequences. Might as well, and recursive for fun. I'm leaving space around the sequence. If you're copying me, I would too. So I got the first sequence, T, 3, 6, 12, 24. The second sequence, S, -7, -2, 3, 8. The third one, R, is 1, -2, 4, -8, dot, dot, dot. That's interesting. It's going back and forth between the pos and neg. And the last one, D, 7, 4, 1, neg 2. Okay, these all look promising because I can kind of tell when it's arithmetic or geometric. In the sequence T, we're just that's a lie. We are not adding 3. What we are doing is multiplying by 2. So that's a geometric sequence. S looks like we are adding 5 every time. So it's arithmetic. R. Oh my goodness. Okay, we are going back and forth. That typically means we're going to be multiplying by a -1 to a power. So like the -1 to an even power would make it positive, and a -1 to a negative power would make it negative. So that's how we can flip back and forth between the negatives. And we're just doubling. So that's going to be some weird -1, and we're also doubling it. That's interesting. But that is geometric because we are multiplying. And here we are subtracting 3, so this is arithmetic. Okay, so we're going to use this indexing process to reindex this, and then we can just bust out the closed forms because we've got formulas for it. So what I mean by that is, instead of calling this the first term, like I did at the beginning of this video, I'm going to reindex this. This series T sub n is going to start at 0 and go to infinity, meaning I have a 0, 1, 2, 3, and so on. I've reindexed it. Similarly, I'll just go ahead and do that to all of these. Typically, these sequences start at 1, but I'm saying, you know what, I want to call this 0. I will do this for arithmetic and geometric sequences, and it may be helpful to do it in other types of sequences as well. And like I said at the beginning, I use the indices to help me come up with the closed form. So I'm going to go ahead and write all my little indices up here. And now they're starting at 0 instead of 1. The sequence has not changed. I've only changed the indices. At the beginning of this, we were thinking of the indices as natural numbers, starting at 1. By doing this, I'm now thinking of the indices as the whole numbers. Same idea, but start at 0. Nothing's really changed too much. Alright, so I claim this is now easy. T sub n is going to be the initial value, 3. And this is geometric, so I'm going to multiply by or let me write that down first. T sub n will be T sub naught times the common ratio to the nth power. So Tn will be the first value, 3, times 3 to the nth power. Okay, let's just double check that. If I plug in 0 for n, that initial value, well, 3 to the 0 is 1. 1 times 3 gives us 3. So far, so good. If I let n be 1, 3 to the first is 3. 3 times 3 is 3. Why am I doing a common ratio of 3? This is doubling values. Why didn't you speak up? Why didn't anyone tell me I was doing that incorrectly? Oh my goodness. This is not 3. The common ratio is 2. If you see me making an error, at least raise your hand next time. Gosh, okay. Is 2. This is a big, lovely 2 right there. Let's try that again. 0. 2 to the 0 power is 1, and 1 times 3 is 3. Yay! 2 to the first power is 2. 2 times 3 is 6. There we go. 2 to the second power is 4. 4 times 3 is 12. 2 to the third power is 8. 8 times 3 is 24. I'm now happy with my closed form. The recursive form is too easy. You just take the previous term and multiply by 2. This is recursive, and this is closed. Okay, let's try that again. I'm adding 5 every single time. This is arithmetic. I've changed the indices starting at 0, so I have a formula for this for the closed form. It says S sub n is equal to the initial value. I've already forgotten. Plus dn. I think it's my bedtime. Plus dn. Plus dn. Plus d times n, where d is the difference. So the difference here is I'm adding 5 every single time. So S sub n will be -7 plus 5 times n. Let's double check that. Last time when I was double checking it, I found my error. So I think it's very smart to double check your work. Let's plug in a 0. Well, 0 times 5 is 0. 0 plus a -7 gives me that initial value. Good. If I plug in a 1, n times 1 is 5. 5 and -7 make -2. Looking good so far. If n is 2, my index here is 2. 5 times 2 is 10. 10 minus 7 is 3. This is good. I claim the recursive is boring. We have S sub n is equal to the previous term plus 5. Okay, this looks really fun. I am multiplying by 2. My common ratio is 2. Is it -2? All right, well, I have just a formula for this. The t sub n is the initial term, t naught, times the common ratio to the nth power. Yeah. So my formula says it's that initial value 1 times, I wish that hadn't been, anyways, times the common ratio to the nth. So every time I'm just multiplying by -2. I was thinking it was going to be harder than this. That's easy. Now my common ratio is -2. Okay, let's triple check this one. If I plug in n for 0, -2 to the 0 power should be 1. 1 times 1 is 1. -2 to the first power is -2. Yep. -2 to the second power makes it a +4. -2 to the third power is a -8. I'm very happy with this. Recursive form. The nth term of the R sequence would be the previous term times -2. Put that in parentheses. Previous term times -2. Good. All right. Let's do this one. This is subtract 3, subtract 3, subtract 3. Arithmetic. That is easy now. I was confused when I was writing it, but now it's easy. All right. Arithmetic. So dn will be equal to the initial term d naught plus dn. Oh, that's not helpful, but dn. That's a different d than that d. Difference. So dn equals 7 plus the difference here is, oh, what is the difference? Because it's not 3, it's a negative 3, I suppose. Maybe we should call that 3 or 7 minus 3n. Okay, that's new to me, so let's double, triple check that. If I plug in 0, well, that goes away, leaving me with 7. If n is 1, I get 4. If n is 2, I get, yeah, this is good. Perfect. And I claim the recursive form should be easy. The nth term of this sequence is simply the previous one times, just kidding, minus 3. All right. So hopefully you see how indexing can be helpful. If you didn't like that, don't you worry about it. Now, what I would like to maybe recognize or talk about here is we are thinking of these sequences as, or I'm for sure am, these indices. So the 0 responds to a -7. The 1 corresponds to a -2. The 2 kind of maps to a 3. The 3 kind of maps to an 8. Do we know of something in math that takes numbers and maps them, or like refers to them as other numbers? Like my input is 2 and the output is 12. My input is 3. My output is 24. These things I called a formula from the very beginning, these closed forms. But this right here, that's just a linear function. These are just functions. I'm taking these natural numbers and they're spitting out real numbers. These happen to all be integers, but that wasn't always the case. But I'm putting in whole numbers and spitting out real numbers. I'm putting in natural numbers and spitting out real numbers. So these sequences can be thought of as functions. Okay, I've got a new definition then for sequence. At the beginning, I was like, oh, they're just a list, an ordered list of numbers. But I got one better now. Sequence. I say it is now a mapping. That's kind of a fancy word for function. From a subset of the integers usually the natural numbers, but I just showed you the whole numbers. To the real numbers. And we said earlier that we can talk about limits. Well, of course that makes sense. Back in Calculus 1, we found limits of functions. So of course we can find the limit of a sequence because these sequences are just a form of a function. So I'm saying this again. I don't know why. I'm just going to put it one more time. If the limit as n approaches infinity of a sequence equals L, a number, we say the sequence converges. I think this is already in your notes, but I'm saying it again. If no such limit exists, we call that divergent. We say a sub n diverges. Bad note taking. All right, let's consider this sequence. All right, this is new. Normally, or so far, I've given you a list of numbers, and then you have come up with the closed form. Now I'm giving you the closed form, and I'm kind of curious, Do you know how to give me the first 4 terms of this thing? Like, can you read this sequence? Can you read the closed form and spit out a sequence? I may even have that in the homework where I give you a closed form or a recursive form, and I'm like, just what are the first 4 terms? But here I think it's maybe pretty obvious. If I plug in 1, I'm going back to the natural numbers as my indexing. I'm not changing the indices. I'm leaving them as starting with 1. So if I plug in 1 here, the reciprocal of 1 is 1. 2 to the negative first power. Well, that's just the reciprocal of 2. Well, that's 1 over 2. Oh, I'm very familiar with this. This is 1 over 3. This is 1 over 4. This is 1 over 5. Dot, dot, dot. Let's graph this. Graph of the sequence A sub n. Here's my y-axis. Doesn't need to be too big. The biggest y value looks like 1. All right, so let me talk about that input and output again. The sequence, we are inputting the natural numbers. So on my x-axis, I'm only really allowed to put those natural numbers. So I'm going to start here at 1, 2, I'm going to at least 5, 3, 4, 5. The function outputs these numbers in the sequence. So the biggest one is 1. Maybe I'll let 4 squares be 1. 2 is a half. 3 is a third. 4 is a fourth. 5 is a fifth. Now, many of you may want to, just by habit, draw a continuous function, and that is not allowed. Continuous function means that we would have a domain of the real numbers. We don't have a domain of the real numbers. Our domain are these indices in, which are the natural numbers. We're only allowed to talk about 1, 2, 3, 4, 5, and so on. Now we did talk about re-indexing, so maybe I could call that a 0 or something, but still, they're discrete numbers. It's not a continuous curve. So this still is a function, though, because it passes that vertical line test. Okay, and I think it's pretty obvious. The limit of this sequence, where is it going? 0. If you don't have a picture, if you're just given a function, well, you can fall back on your Cal 1 skills and you can find the limit of a function. So a sub n, its closed form is n to the negative 1. So I can find the limit as n goes out to infinity of n to the negative first power. I then want to, I just want to call that 1 over n. And how do we evaluate limits? This is long, old-timey days. Well, you direct substitute and hope it works. So I'm going to direct substitute 1 over infinity, and we say, oh yeah, that's okay. In the limiting process, this will go to 0. All right, that's our next area. Now that we can think of sequences as functions, maybe not continuous ones, but at least discrete functions, we can go back and kind of review our limit skills. Let's do that. Let's do some more of these examples. So for the next examples, I want to just find the limit if they exist. use this set/sequence notation, but I'm going to give you the closed form. N to the 12th over 3n to the 12th plus 4. This is a closed form of the sequence. So it's probably just a good practice whenever you get one of these to just make sure you can get the first 4 terms. So if n is 1, that's easy to do. You get 1 over 7. Well, that's going to be, okay, never mind. At least the first term, because 2 is going to be nasty. 2 to the 12th power is way too big. Hey, but I found the first term. This is the first term. If the exponent's not so big, try to find a few terms to make sense of the sequence. But I can tell you that this thing is going to get bigger, and that thing is going to get bigger faster. We've done this before. We've talked about this before. I'm going to evaluate the limit as this n gets bigger and bigger or goes to infinity, and I'm going to treat this sequence like a function because it is. How do you find limits? I, when tasked, try direct substitution, and I hope and pray that I get a number. If I get a number, like 1 over 6, then I know that this sequence will be approaching 1 over 6, the limit exists, and I'm done. Let's see what happens. Oh, that sounds very familiar. We call that a ratio indeterminate. My notation, I put a little asterisk there to remind myself that this limit, it's okay to apply L'Hopital's rule. Fun. This is some old school review. I love these types of problems. Let's see. L'Hopital says the limit of this function is equal to another limit of a different function, and the different function is still a ratio, but the derivative of the numerator and the derivative of the denominator separately, not some kind of quotient rule. Don't get confused. L'Hopital's rule is you do it independently. So up top, the derivative of n to the 12th power is 12n to the 11th power. Down below, 3 times 12 is 36. This is now n to the 11th, and the 4 goes to 0, which is nice, meaning I can do some reduction. Before you try to direct substitute, you always reduce. If I direct substitute right this minute, I'll have another infinity over infinity, and I'll have to apply L'Hopital maybe 10 more times. So you always try to simplify if at all possible. And I have some simplification I can do because I can reduce. 12 over 36 is 1/3, and the n's completely reduce. Oh, and the limit of a number is that number. Oh man, if you have forgotten this stuff, just go back and watch those old videos. But hopefully it's just coming back to you. Another way to do this, just while I have your attention, maybe the L'Hopital's scenario is not created. Don't forget there are algebraic ways around this as well. Basically, the n to the 12th is in the way. It's causing problems. So we can get rid of it by going through and multiplying by a form of 1 over n to the 12th. All I'm doing is multiplying by 1. And n is just some number way out there. So n is not 0 or something. So this is totally legal. This is equal to a different limit. This is the very first property of limits we learned in Cal 1, that you can change that function with legal math, and those limits will be equal. It's like our favorite property. Okay, up top we get a 1. Down below we can distribute 3 plus, and this will be 4 over n to the 12th. Now when I direct substitute, I have 1 over 3 plus 4 over infinity. This is kind of nonsense, but in this limiting process, 4 over infinite is going to 0. So we get the 1/3. Oh yeah, so the whole point of this was to find a limit. Yes, the limit exists. This sequence is approaching, or it's going toward 1/3. When we did this type of talk back in the day, we would say because the limit exists at the end as n approaches infinity, that means therefore there exists a horizontal asymptote at that number, y equals 1/3. Remember that? Meaning if we were to graph this discrete function, that it would have a horizontal asymptote at 1/3 because the function is approaching the 1/3. All right, that was reviewing some limit skills. Let's do that again. Let's try and find the limit as n goes to infinity of this. I'm calling it a sequence, but really this is just a calculus 1 problem where this could have been a function I gave you. Let me try to do that again. I've got this binomial 1 plus 4 over n that's being raised to the 3nth power. I want to find the limit of this thing as n approaches infinity. As n gets bigger, what does this sequence do? In the previous example, I said if you could get the first few terms of the sequence, that may be just helpful. Last time I could only get 1 over 7, but let's see if I can do more. If n is 1, well, 1 plus 4 is 5. 5 to the 3rd power is 125. Oh man, this gets big so fast. I'm going to grab a calculator to help me with the next one. No, that's not too bad. 4 over 2 is 2. 2 plus 1 is 3. 3 to the 6th power. I should know that. 3 to the 6th power. Oh yeah, 729. Five cubed, and then what was that? Okay. So I think I already know this thing is probably diverging just from my educated guess. It jumped up a lot, but who knows? Maybe it gets smaller. I don't know. All right. Well, it's just a limit, so I can evaluate a limit. I try direct substitution. If I get a number like 5 million, then I'm done. So let's direct substitute, hope and pray this works. 1 plus 4 over infinity being raised to 3 times infinity. Oh, I could simplify that to 1 plus 0 to the infinite power, which is 1 to the infinite power. Ooh, Power indeterminate. Yay! Power indeterminate. Okay, this is not L'Hopital's rule. This is logarithms need to come into play here. The way we handle a power indeterminate is we let the function reset y equal to this function, and then we get rid of the power by taking the natural log of both sides and using a power rule of logs to pull it down. I'm going to let my notes say something crazy, but I'm going to let y equal this function, 1 plus 4 over n to the 3nth power. I dropped the limit notation. So I've said I'm not doing that problem. What I'm going to do is I'm going to talk about the function itself, and I'm going to take the natural log of both sides. This is review. The log has a power of 3n, so I can roll it off the log and treat it as a coefficient. All right, I need to reintroduce the limit notation. So just like you can take the natural log of both sides, you can think of it as I'm evaluating the limit as n approaches infinity of both sides. That's a legal way to think about it. If this has been a while for you and you're scared, just go back and look at power indeterminates from your Cal 1 course. Okay, now this is so much fun. This is where we break the problem again. So we already broke it once. We're breaking it again, and we're going to go off and just focus in on this right-hand side. So I will come back to this left-hand side later. Love you, but we'll be back later. Let's focus in on orange stuff. Okay, it's just a limit. I know how to evaluate limits. You direct substitute and hope and pray. So I'm going to direct substitute natural log of 1 over 4 over n. Did I drop a 3n? I sure did. Thought that might be too easy. What happened to my 3n? It's sitting right there. I got too happy. Try that again. 3n times the natural log of 1 over 4 over n. I hope and pray that this thing, when I just shove in a infinity, everything just works out. So I go and I get 3 times infinity times the natural log of 1 plus 4 over infinity. Okay, well this is going to be infinity times the natural log of 1. Oh my goodness. This is infinity times 0. Bonkers! That's another indeterminate. Wow, we're reviewing everything. We had a ratio indeterminate. That was fun in L'Hopital's. We had a power indeterminate. We rewrote it. Now it's a product indeterminate. We don't know how to handle that, but the way we do handle it is we rewrite the product as a quotient. If I can take this orange mess and instead of multiplying the things together and getting a nonsense, if I can put it as a quotient, divide the things, and get infinity over infinity or 0 over 0, then I could go back and apply L'Hopital's rule to that orange stuff and hope it turns out that way. So let's do that. Instead of multiplying 3n times the natural log, I can reciprocate probably the n I don't want to reciprocate a natural log. That kind of scares me for some reason. So I'm going to rewrite this. Instead of 3 times n times the natural log, I'm going to say 3 times the natural log over n, changing the power to a negative 1. Oh, I could just pull the 3. Oh well, let it in there. Okay, so the strategy for the product indeterminants, we don't know what infinity times 0 is to rewrite the product as a quotient. Maybe now we'll get something that we know. I'm going to try direct substitution again in this form. So I get 3 times, and we said this is going to be 0 up top. Down below I have 1 over n. Well, that's 1 over infinity. And that's nonsense, but in this limiting idea, it is 0. So I am getting 0 over 0. So in this form, I can apply my asterisk. Let me grab a different color. And that's just my notation to let me know that in this form, I can apply L'Hopital's rule. Oh my goodness, I'm running out of paper. Let's see. And I'm still just kind of glossing over the fact that I've ignored the purple stuff. I'm only dealing with the right-hand side of the equation at this moment. Okay, so that means I can come down here and I can apply L'Hopital's rule. L'Hopital's rule says if you direct substitute and you get infinity over infinity or 0 over 0, that limit will be equal to another limit where you take the derivative of the numerator divided by the derivative of the denominator. Well, I can do that. Up top, 3 is just going to be a constant that I can pull out, so it's still there. The derivative of the natural log is 1 over the argument times the derivative of the argument. Okay, I can do that. I'm going to put 3 over the argument, 1 plus 4 over n is what I should have written there. That's an n. Sorry, I got so excited. I'm having too much fun. That's an n, and when I rewrote it as an infinity, yeah, okay. That's an n. I have 4 over n, but I do still need to handle the derivative of 1 plus 4 over n. I'll leave that for a rainy day. All over. The derivative down below is a power rule. Just in derivatives. Power rule back in the old days. You pull down the power, rewrite the base, and you subtract 1 from the power. I still have this chain rule to take care of. I'm going to move this, giving more room. I'm not done with the derivative process. Okay, well, the derivative of 1 is nothing. I don't have to worry about it. And this is just 4 into the negative firsts. So I can take the derivative of that. That's just going to be a negative 4 into the negative second power. Oh, that's going to be so much fun. Oh my God, do you see what I see? Do you see what I see? Bye. Goodbye. Doop 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 booty boo doo boo doo doo. This video has been really long. Okay, now I have simplified it. I think that's as far as I can simplify. I'm ready for direct substitution. Still, there's this purple stuff. Let's not forget about that. But direct substituting on the right-hand side, evaluating this limit, I'm hoping and praying a number spits out. 12 over 1 plus 4 over infinity. Well, that kind of goes to 12 over 1. Oh, that's just a lovely 12. Do you remember the shortcut for this now? If not, that's okay. It's just some properties of limits and logs that we just accept to be true. If you have the limit of the natural log of something, you can rewrite this. That is a property of limits. So I'm going to call this the natural log of the limit as n goes to infinity of y. Let's not forget that our original quest was to find the limit of this thing as it went to infinity. And we said, no, I don't want to do that. What I want to do is instead talk about y being that function and playing around with it. Well, my task was to find the limit as n goes to infinity of y. This is y. So the limit as n goes to infinity of y. That's what I have right here. The limit as n goes to infinity of y. But there's this weird natural log in my way. Oh, the definition of the logarithm is how we end this disaster. We go, the base e being raised to the 12th power will equal what we're after this limit. E to the 12th equals the limit as n approaches infinity of y, where y was my original function 1 plus 4 over n being raised to the 3nth power. E to the 12th. Limit does exist. This function is approaching a number, e to the 12th power. It does converge to e to the 12th power. It does have a horizontal asymptote. Bam! It's been a long video. I may have to upload it and paste those. Let's see here. Is there anything else I want to do? I think I will leave that for an exercise in the homework. So, there's a lot going on today, but there you go. Sequences, an ordered list of numbers. We think about it as first, second, third, fourth. So therefore, we can think about the first is this, the second is this. So we can think about it as a function. We can apply all of our function talk like we normally would. A sequence can converge, meaning it has a limit. All those old skills are coming back to you. This is a good, nice review of the calculus sequence. We're going to continue with this idea of discrete mathematics as we continue on into the sequences and series coming up next talk. Okay, go to the homework. See you in the next video.